In early 1945, in the waters off Japan's coast, an American F4U Corsair ditched. The plane went down after engine failure during combat operations, and its pilot ejected as the fighter hit the cold Pacific. Japanese patrol boats converged on the floating wreckage within hours. What they recovered would become one of the most significant intelligence opportunities in the war's final months. For nearly 3 years, Japanese pilots had faced this American fighter in the skies over the Solomon Islands, Rabaul, the Philippines, and now the home islands. They had learned to respect its speed, its firepower, and its seemingly indestructible construction. But they had never before possessed an intact example to examine in detail, to measure, to test, and to truly understand how far they had fallen behind. The story of Japan's encounter with the F4U Corsair is not merely a tale of a captured aircraft. It's the chronicle of a nation's technological awakening. It marks the moment when Japan's aviation specialists confronted the full magnitude of American industrial and engineering superiority. By examining this fighter, they would discover truths about manufacturing precision, materials science, and design philosophy that shattered assumptions about their own capabilities. The Corsair recovered by Japanese salvage crews represented the culmination of American fighter development. Designed in 1938 to meet the United States Navy's demanding specifications, the F4U had evolved from a radical concept into one of the war's most feared combat aircraft. Its distinctive inverted gull wing, massive Pratt and Whitney R2800 double Wasp engine, and revolutionary performance characteristics made it instantly recognizable. More importantly, it had achieved a balance between speed, firepower, range, and structural strength, something Japanese aviation struggled to match. The Corsair's genesis dated to 1938 when the Navy's Bureau of Aeronautics requested a fighter capable of exceeding $400 tax-per in level flight. This specification alone was revolutionary, as most fighter aircraft at the time struggled to reach $350 text mast. Beyond speed, the Navy demanded a complete package: low stalling speed for carrier operations, $1,000 hard text dials mid-range, heavy armament, and the ability to carry bombs. Chance Vaught's response was audacious. Chief designer Rex Beazle and his team decided to build their aircraft around the largest, most powerful engine available, the Pratt & Whitney R2800 double Wasp. This 18-cylinder, two-row radial engine produced $2,000 horsepower, nearly double that of most contemporary fighters. To harness this power, they designed a massive $13 FT, 4-on text in dollar diameter propeller, the largest ever fitted to a fighter aircraft. The engineering challenge was immediate. How to provide ground clearance for such a large propeller while maintaining structural efficiency for carrier operations. The solution became the Corsair's most distinctive feature. Instead of using conventional straight wings, Beazle's team created an inverted gull wing design. The wings angled downward from the fuselage before leveling out, creating a distinctive M shape when viewed from the front. This configuration allowed for relatively short landing gear while still providing propeller clearance. The anhedral angle where the wing met the fuselage also created optimal aerodynamic conditions, minimizing drag. The prototype, the XF4U-1, flew on May 29, 1940, piloted by Vought's chief test pilot, Lyman Abulard Jr., from the factory airfield in Stratford, Connecticut. It made history. On October 1, 1940, during a test flight, the XF4U-1 achieved a ground speed of $405 text-per with tailwind assistance, making headlines as the first single-engine American fighter to reach this milestone. Its actual maximum level flight speed was $378 text-mem-taz at $23,500 text-ft-taz. Still exceptional performance for 1940 production F4U-1. Corsairs began reaching operational units in late 1942. Marine Fighter Squadron. VMF-124 received the first combat-ready aircraft, deploying to Henderson Field, Guadalcanal, on February 12, 1943. The Corsair's combat debut proved inauspicious. On February 14, 1943, during what became known as the St. Valentine's Day Massacre, Corsairs suffered a disastrous first engagement. 9 American aircraft were lost, including 2 Corsairs, multiple P-38 Lightnings, P-40 Warhawks, and bombers, while Japanese defenders lost only a single Zero fighter. The $9.1 loss ratio in Japan's favor was so severe that daylight bombing missions to Bougainville were suspended pending tactical reassessment. This engagement demonstrated that superior technology alone could not guarantee victory. Tactics, experience, and proper deployment mattered equally. American pilots adapted quickly. They learned that the Corsair's strength lay not in dogfighting, but in what became known as boom and zoom tactics. While the Corsair couldn't outturn a Zero in slow-speed maneuvering, it could outdive, outclimb, and outrun any Japanese fighter. Proper tactics meant maintaining speed and altitude advantage, diving on enemy aircraft, firing, and using superior speed to disengage before the enemy could respond. Second Lieutenant Kenneth A. Walsh of VMF 124 became the first Corsair ace on May 13, 1943, mastering these tactics and eventually achieving 21 victories. As the war progressed through 1943 and 1944, the Corsair's reputation grew. Marine squadrons in the Solomon Islands, flying from hastily constructed coral airstrips, exploited the aircraft's ruggedness to devastating effect. The Corsair proved capable of absorbing battle damage that would have destroyed lighter Japanese fighters. Its 6 50 text its caliber or Browning machine guns provided overwhelming firepower, the 4 inboard guns carrying 400 rounds each, and the 2 outboard guns carrying 375 rounds each, totaling 2,350 rounds. Later variants, like the F4U 1C, replaced the machine guns with 420 text M cannons, though many pilots preferred the reliability and ammunition capacity of the 50 Hontext caliber's weapons. The Corsair's versatility extended beyond air combat. By mid-1944, Corsairs regularly carried external ordnance, $1,000 text LB bombs on centerline and wing racks, 8 $5 text in high-velocity aircraft rockets, or napalm canisters. This fighter bomber capability made the Corsair invaluable for close air support during amphibious operations. During the Okinawa campaign in 1945, Corsairs flew thousands of ground attack sorties, earning the nickname Angels of Okinawa from grateful infantrymen. The combat experiences of Japanese pilots told only part of the Corsair's story. From the cockpit of a Zero, a pilot saw an opponent that was stronger, faster, and more resilient. But understanding the engineering and manufacturing techniques behind these advantages required a physical examination of the aircraft itself. Japan's capability for such technical analysis centered on 2 facilities: the Yokosuka Naval Air Technical Arsenal, south of Tokyo, and the Army Aviation Technical Research Institute at Tachikawa. These organizations had been examining captured Allied aircraft throughout the war, but most were damaged or incomplete wrecks. An intact operational example of a frontline American fighter represented an extraordinary opportunity. The salvaged Corsair arrived at Yokosuka in early 1945, though it had suffered water damage during its forced landing. The basic structure remained sound. Recovery teams worked to prevent complete sinking, and the fighter was transported to Yokosuka's secure technical area. This was crucial, as previous Allied aircraft captures were often heavily damaged, making it difficult to distinguish design features from battle damage. Japanese specialists began with systematic photography and measurement. Every dimension was recorded: wingspan of $40 hardtext feet, 11.7 hardtext in hour, length of 33 textamer feet, 4 itextum in, and height of 15 DARS adern text, FT DARS with wings extended. The inverted gull wing configuration immediately drew attention. Japanese designers recognized its aerodynamic and structural advantages, but also its manufacturing complexity, requiring sophisticated tooling and quality control beyond what most Japanese factories could reliably achieve at that stage of the war. The examination revealed a surprise. Despite the Corsair's advanced nature, portions of its outer wing surfaces were covered with fabric rather than metal, aft of the main wing spar and armament bays, including control surfaces. Initially puzzling, further analysis revealed a sophisticated reality. The fabric covering was a deliberate design choice from the 1938-1940 development period. It reduced weight where structural loads were minimal, saving aluminum for critical load-bearing components. This represented a mature understanding of resource allocation for optimal performance. Disassembly of the wing structure revealed construction methods that technical personnel found both impressive and troubling. The main wing spar, the critical structural element, was a massive forging of exceptional quality. American metallurgy had produced aluminum alloy forgings with strength characteristics that Japanese facilities struggled to match. This single component illustrated a fundamental difference. American industry could produce large, complex forgings with consistent quality, while Japanese manufacturers increasingly relied on built-up structures assembled from smaller components. The wing's internal structure showed similar sophistication, with ribs stamped from aluminum sheet demonstrating remarkable precision and consistency, indicative of manufacturing processes with tight quality control. Japanese aircraft production, conversely, increasingly struggled with consistency as the war progressed. Attention turned to the Corsair's armament installation. The $6,050 Texta caliber of Browning AN-M2 machine guns represented formidable firepower. The installation was compact, reliable, and designed for easy maintenance. Japanese examiners were struck not just by the firepower, but by the system's completeness. Ammunition boxes, feed systems, spent cartridge ejection, and charging mechanisms were all engineered to work seamlessly. The guns themselves were specimens of precision manufacturing. American ordnance production had achieved reliability levels that Japanese industry envied. The discovery of $150 text $LB of armor plate protecting the cockpit and a 1.5 ounce text in $, thick bullet-resistant glass panel behind the windscreen reinforced impressions of American design philosophy. Japanese fighters had largely abandoned heavy armor protection for lighter weight and better maneuverability. The Corsair demonstrated that proper engineering, made possible by the massive power of the R2800 engine, could incorporate substantial protective armor without sacrificing performance. The Pratt & Whitney R2800 double Wasp engine dominated the technical examination. This 18-cylinder, two-row radial, displacing $2,800 of text cubic inches dollars and producing over $2,000 horsepower, was a masterpiece of mechanical engineering. Japanese engineers had encountered it before, but never in good condition for thorough analysis. The engine's construction revealed manufacturing capabilities that seemed almost incomprehensible. Cylinders were precisely machined with tolerances measured in thousandths of an inch. Pistons, connecting rods, and crankshaft components showed surface finishes and dimensional accuracy that Japanese engine manufacturers struggled to achieve. The two-stage supercharger system, designed to maintain power at high altitudes, incorporated complex internal passages and precisely fitted rotating components. Japanese attempts to develop comparable supercharger systems had largely failed due to manufacturing limitations. Perhaps most impressive was the engine's reliability and power output. American radial engines routinely produced their rated horsepower for hundreds of hours between overhauls, a consistent performance that came from superior metallurgy, better lubricants, more precise manufacturing, and more sophisticated quality control. Examination of systems throughout the aircraft revealed consistent patterns. Landing gear, complex but precisely manufactured mechanism. Cockpit, comprehensive arrays of gauges and controls, exceeding anything in Japanese fighters. Fuel system, incorporated self-sealing tanks using multiple rubber compound layers that swelled when punctured, preventing catastrophic fuel loss, a technology Japanese aircraft largely lacked. Electrical system, powered extensive equipment through high-quality wiring with proper insulation and organization. Perhaps most revealing was the overall quality of materials and manufacturing. Every component, from major structural elements to small fasteners, showed consistent quality. Aluminum alloys had uniform properties, steels were properly heat-treated, and surface finishes were smooth and professional. The aircraft felt substantial, well-made, and built to last. This overall quality stood in sharp contrast to Japanese aircraft production in 1945, which was suffering from wartime shortages, deteriorating aluminum quality, conscripted skilled workers, and a demand for quantity over quality under constant threat of American air raids. The examination of the captured Corsair occurred as Japan faced imminent defeat. In this desperate context, the Corsair examination took on somber significance. It was not intelligence gathering for future victories, but a final reckoning with technological reality. Japanese engineers at Yokosuka and Tachikawa wrote technical reports documenting their findings, detailing measurements, describing manufacturing techniques, and offering assessments of American capabilities. The tone was professional, but could not hide the underlying implications. In nearly every category examined, American technology exceeded Japanese capabilities. The gap was not small or easily closed. It represented years of industrial development, massive investments in research and tooling, sophisticated supply chains, and resources Japan simply did not possess. By war's end in August 1945, at least 2 Corsairs had been captured by Japanese forces. Evidence suggests technical personnel repaired at least 1 aircraft toward flying condition, indicating serious efforts to make the aircraft operational for evaluation, although actual flight testing remains uncertain. When American occupation forces arrived at the Yokosuka Naval Air Technical Arsenal in September 1945, they found extensive evidence of Japanese technical intelligence efforts. Technical reports, drawings, and photographs documented Japanese attempts to understand Allied technology, the story of the Japanese. Examination of the F4U Corsair symbolizes the vast gulf separating American and Japanese aviation by war's end. When the Corsair first entered combat in early 1943, Japanese pilots in Zero fighters could still compete effectively through superior tactics and pilot skill. By 1945, even experienced Japanese pilots in more modern aircraft stood little chance against well-flown Corsairs. The aircraft's technological advantages, combined with overwhelming American numerical superiority and better pilot training, created impossible odds. The Corsair achieved an official kill ratio of 11.1 against Japanese aircraft, with American pilots shooting down 2,040 Japanese aircraft while losing only 189 Corsairs to enemy action during World War II. Japanese engineers examining the captured Corsair understood all of this. They could measure the performance gap, analyze the manufacturing differences, and calculate the resource disparities. Their reports documenting these findings stand as acknowledgments of Japan's failed attempt to match American industrial might. The Corsair itself went on to long service beyond World War II, fighting in the Korean War, 1950-1953, and in colonial conflicts, flown by foreign air forces through the 1960s. The last combat missions by a Corsair occurred in July 1969 during the brief Massacre war between Honduras and El Salvador. For Japan, the encounter with the Corsair was part of a larger reckoning with technological reality during the American occupation. Lessons learned from examining American technology, including the Corsair, influenced post-war Japanese manufacturing philosophy. The emphasis on quality, precision manufacturing, and continuous improvement that characterizes modern Japanese industry has roots in the hard lessons learned when Japanese engineers examined what American industry could produce. The Corsair recovered. In early 1945 represented more than a downed fighter. It was evidence of engineering excellence and manufacturing sophistication that Japanese aviation had been seeking throughout the war. The lessons it taught came too late to change the war's outcome, but they helped shape the peace that followed. In examining this American fighter, Japanese engineers confronted the full magnitude of the challenge Japan had faced. They had fought with skill and courage, but courage and skill could not overcome the massive technological and industrial advantages their opponent possessed. The story ends not with triumph, but with acknowledgement. The Japanese technical reports on the Corsair serve as silent witnesses to a moment when one nation's engineers confronted another nation's capabilities. The Corsair they examined has long since vanished, but its legacy remains in the lessons it taught about what technology, properly applied with adequate resources and sophisticated manufacturing, could achieve. Japanese engineers would never again underestimate what their American counterparts could accomplish when given the industrial capacity, scientific knowledge, and resources to fully realize their designs. The examination of the F4U Corsair by Japanese technical personnel in 1945 stands as a watershed moment, the point when Japan's aviation establishment fully grasped the technological chasm that had opened during the war years. It was a lesson written not in propaganda or combat reports, but in aluminum alloys, precision forgings, and manufacturing tolerances that spoke louder than any words could about the true nature of American industrial power.